Here's the second part of waves. We're now going to start talking about interference. Interference patterns occur when waves from different sources arrive at the same point at the same time. A material object will not share its space with another object, but more than one wave can exist at the same time in the same space. If you drop two rocks in water, the waves produced by each can overlap and form an interference pattern. An interference pattern is a regular arrangement of waves where wave effects are increased, decreased, or neutralized. In constructive interference, the crest of one wave overlaps the crest of another wave and their individual effects add together. The result is a wave of increased amplitude called reinforcement. In destructive interference, the crest of one wave overlaps the trough of another wave and their individual effects are reduced. The high part of one wave fills in the lower part of another called cancellation. In constructive interference, the waves reinforce each other to produce a wave of increased amplitude. You notice that this one is higher than the other two. In destructive interference, the waves cancel each other and no wave is produced. You see how these are exact opposites of one another? You get cancellation. They both cancel out. Wave interference is easiest to see in water as an interference pattern. When waves are out of phase, the crest of one wave overlaps the trough of another to produce rains of zero amplitude. When waves are in phase, the crests of one wave overlap the crests of another, and the troughs overlap. You get much higher waves. Two overlapping water waves produce an interference pattern. See that one? Overlapping concentric circles produce a pictorial representation of an interference pattern. Interference patterns are nicely illustrated by overlapping or concentric circles printed on a pair of pier sheets. Then when the sheets overlap with their centers slightly apart, a pattern is formed similar to the interference pattern of waves. A slight shift in the sheets produces noticeably different patterns. Interference is characteristic of all wave motion, where the waves are water waves, sound waves, or light waves. All of these can have interference. So what causes interference patterns? A standing wave forms only if half a wavelength or a multiple of a half of a wavelength fits exactly into the length of the vibrating medium. And we'll talk more about this. Produce a wave by tying a rope to a wall and shaking the free end up and down. The wave reflects back along the rope to you. By shaking the rope just right, you can cause the incident, origin, and reflected waves to form a standing wave. A standing wave is a wave that appears to stay in one place. It does not seem to move through the medium. Certain parts of a standing wave remain stationary. Nodes are the stationary parts on a standing wave. Hold your fingers on either side of the rope at a node, and the rope will not touch them. The positions on a standing wave with the largest amplitudes are known as antinodes. Antinodes occur halfway between two nodes. Standing waves are the result of interference. When two waves of equal amplitude and wavelength pass through each other in opposite directions, the waves are always out of phase at the nodes. The nodes are stable regions of destructive interference. The incident and reflected waves interfere to produce a standing wave. The nodes are places that remain stationary. So if you look at our pictures here, this is going to be the node for all of them as it goes up here, because at that point, that point never leaves the midpoint. You can produce a variety of standing waves by shaking the room at different frequencies. Once you find a frequency that produces a standing wave, double or triple the frequency will also produce a standing wave. If you shake the rope until you see a standing wave of half a wavelength, because it only goes one way up. A full wavelength would be like this. Right here, what they're showing right there is just half a wavelength. Shake the rope until you set up a standing wave of half a wavelength, then shake it with twice the frequency and produce a standing wave with one wavelength. So we went from this half a wavelength to a full wavelength. Now if we shake with 3 times the frequency and produce a standing wave with 1.5 wavelengths. So we got a full wavelength plus a half another. Standing waves are set up in the strings of musical instruments that are struck. They are set up in the air in the organ pipes in the air of a soda pop bottle when air is blown over the top. Standing waves can be produced in either transverse or longitudinal waves. Is it possible for one wave to cancel another wave so that the combined amplitude is zero? Explain your answer. Yes, this is called destructive interference in a standing wave. For example, parts of the wave have no amplitude at the nodes. At what wavelengths can a standing wave form in a vibrating medium? As a wave source approaches, an observer encounters waves with a higher frequency. As the wave source moves away, an observer encounters waves with a lower frequency. This is called the Doppler effect. You've probably heard of this before, but might not know what it is. Imagine a bug jiggling its legs and bobbing up and down in the middle of a quiet puddle. The crest of the wave it makes are concentric circles because the wave speed is the same in all directions. If the bug bobs in the water at constant frequency, the wavelength will be the same for all successive waves. The wave frequency is the same as the bug's bobbing frequency. Suppose the jiggling bug moves across the water at a speed that is less than the wave speed. The wave pattern is distorted and is no longer concentric. The center of the outer crest is made when the bug is at the center of that circle. The center of the next smaller crest will be made when the bug was at the center of the circle, and so forth. The bug maintains the same bobbing frequency as before. However, an observer would encounter a higher frequency if the bug is moving towards the observer. This is because of the successive crests has a shorter distance to travel, so they arrive more frequently. If the bug is moving away from the observer, on the other hand, there is a lower frequency. There is a longer time between wave crests. Each crest has to travel farther than the one ahead of it due to the bug's motion. This apparent change in frequency due to the motion of the source or receiver is called the Doppler effect. The greater the speed of the source, the greater will be the Doppler effect. The Doppler effect causes the change in pitch of a siren. When a fire truck approaches, the pitch sounds higher than normal because the sound wave crests arrive more frequently. When the truck passes and moves away, you hear a drop in pitch because the wave crests are arriving less frequently. So if you see these lines right here, they're much closer together. You hear a higher frequency. Once it passes you, you're going to hear a lower frequency. Police use the Doppler effect of radar waves to measure the speeds of cars on the highway. Radar waves are electromagnetic waves. Police bounce them off cars. A computer built into the radar system compares the frequency of the radar with the frequency of the reflected waves to find the speed of the car. The Doppler effect also occurs for light. When a light source approaches, there is an increase in its measured frequency. When it recedes, there is a decrease in its frequency. Increased frequency is called a blue shift because the increases towards the higher frequency are blue end of the spectrum. Decreasing frequency is called a red shift, referring to the low frequency or red end of the color spectrum. Distant galaxies show a red shift in their light. A measurement of this shift enables astronomers to calculate their speeds of recession. When a source moves towards you, do you measure an increase or decrease in wave speed? Neither. It is the frequency of the wave that undergoes a change, not the wave speed. Good thing to remember. How does the apparent frequency of a wave change as a wave source moves? All right, bow waves. Bow waves occur when a wave source moves faster than the wave it produces. When the speed of the source in a medium is as great as the speed of the wave it produces, something interesting happens. The waves pile up. If the bug swims as fast as the wave speed, it will keep up with the wave crests it produces. The bug moves right along with the leading edge of the wave it is producing. The same thing happens when an aircraft travels at the speed of sound. The overlapping wave crests disrupt the airflow of the air over the wings so that it's harder to control the plane when it's close to flying the speed of sound. When the plane travels faster than sound, it is supersonic. A supersonic plane flies into a smooth, undisturbed air because no sound wave can propagate out in the front of it. Similarly, a bug swimming faster than the speed of water waves is always entering into water with smooth, unrippled surface. When the bug swims faster than wave speed, it outruns the wave crests it produces. The crests overlap at the edges, and the pattern made by these overlap crests is a V shape. called a bow wave. The bow wave appears to be dragging behind the bug. The familiar bow wave generated by a speedboat is produced by overlapping of many circular wave crests. Bow wave. V equals the speed of the bug. VW is the wave speed. The wave patterns made by a bug swimming at successively greater speeds change, overlapping at the edges, occurs only when the source travels faster than the wave speed. And here you have your examples of how fast they go. What causes a bow wave? Shock waves. A shock wave occurs when an object moves faster than the speed of sound. A speedboat knifing through the water generates a two-dimensional bow wave. A supersonic aircraft similarly generates a shock wave. A shock wave is a three-dimensional wave that consists of overlapping spheres that form a cone. The conical shock wave generated by a supersonic craft speeds or spreads until it reaches the ground. The bow wave of a speedboat that passes by can splash and douse you if you are at the water's edge. In a sense, you can say that you are hit by a water boom. In the same sense, a conical shell of compressed air sweeps behind a supersonic aircraft. The sharp crack heard when the shock wave that sweeps behind a supersonic aircraft reaches the listener, it's called a sonic boom. We don't hear a sonic boom from a subsonic aircraft. The sound wave crests reach our ears one at a time and are perceived as a continuous one. Only when the craft moves faster than sound do the crests overlap and encounter the listener in a single burst. Ears cannot distinguish between the high pressure from an explosion and the pressure from an overlapping wave crest. A common misconception is that the sonic booms are produced only at the moment that the aircraft surpasses the speed of sound. In fact, a shock wave and its resulting sonic boom are swept continuously behind an aircraft traveling faster than sound. The shock wave has not yet encountered listener C, but is now encountering listener B and has already passed listener A. A supersonic bullet passes overhead, produces a crack, which is a small sonic boom. When a lion tamer cracks a circus whip, the cracking sound is actually a sonic boom produced by the tip of the whip. Snap a towel, and the end of the towel can exceed the speed of sound and produce a mini sonic boom. The bullet, the whip, and the towel are not in themselves sound sources. When they travel at the supersonic speeds, sound is generated as waves of air at the sides of the moving object. What causes a shock wave? Here is the end of our notes.